Okay, good day, students. Today we're going to talk about design of seismic resistant steel buildings and structures. So, primary focus of this presentation is on ductile detailing of the steel structures for seismic resistance. In general, discussion of the basic principles of the behavior of seismic response of steel structures. A brief review of causes of earthquakes and its effects on the buildings and structures, which include discussions of seismic hazards, maps, and the basic concept of dynamic response of the structure. So, introduction to the seismic load resistant systems, resisting frames, concentrically braced frames, eccentrically braced frames, buckling restrained braced frames, and other special plates, steel plates actually. So, performance of steel buildings in past earthquakes. When considering the performance of the steel buildings in the past earthquakes, it is instructive to make the first look at causes, fatalities in earthquakes. This slide shows us an analysis of the causes of fatalities in earthquakes for the period of 19th century to 1949. And the second period is from 1950 to 1990. So, some observations. The primary causes of the earthquakes fatalities is collapses of the building. Consequently, structural engineers play a leading role to prevent the earthquake fatalities by the right design and the calculation of the building, by the right construction of the building, by the right operational using the building during the lifetime of the building. Among the building collapses, the primary cause of the fatalities is collapse, as you see, of the masonry buildings. So these are primarily and reinforcement masonry or non-engineered masonry buildings. As we know, the masonry buildings can be considered like one of the non-protected buildings from the earthquakes, because there are no reinforcing, there are no rigid connections, there are no other additional seismic resistant frames included into this construction. That's why the results of the buildings made from the masonry is so higher actually in comparison with other ones. The period from 1950 to 1990 show us increasing number of fatalities from the collapse of engineered structures. So particularly reinforced concrete structures. So as compared with 1949, from 1900 to 1949. So what we can say that when reinforced concrete and reinforced masonry structures are designed and detailed for the seismic resistance, so the per current buildings codes. Actually, in each country there are the special regulations and recommendations for the codes. The performance in earthquakes shows the good results. So the data in these slides reflects the masonry and the reinforcement reflects the masonry and reinforcement concrete buildings that are not well engineered for seismic resistance. What about other causes of fatalities? They include post-earthquake fires, landslides, and tsunamis. So if we'll talk about steel structures, structures actually have historically performed well in earthquakes and showed a little loss of life can be attributed to the collapse of the steel buildings in earthquakes. This good track record can likely be attributed in several causes. Steel structures, firstly, generally lighter than, for instance, masonry construction and the reinforcement concrete construction. So, and we know the low weight translates to low seismic forces. More late construction, so more it will affect by the seismic loads. Still, secondly, steel structures typically show good ductility, even when they are not specifically designed or detailedly designed for the seismic resistance. That's very important because sometimes in places where there are no seismical activities, but it happens. Moreover, steel structures showed the good results in comparison with the other typical structures which are made by the other materials. And the third, many of the highly destructive earthquakes, so around the world actually, occurred in areas where was a very little or very short number of the steel structures. Thus, the exposure of steel structures to strong earthquakes has been perhaps somewhat less than other types of construction. But despite the showing of this slide, overall good performance in the past earthquakes showed the modern welded buildings and the increasing number of the problems in recent earthquakes. So the next few slides will illustrate the same examples of the earthquakes which was collapsed. And the first example is the Mexico City. So this earthquake was in the 1985. So the building was consist of five still. The complex of buildings consists of five steel buildings. There was three buildings, 21-story buildings, and two buildings, 14-story buildings. So one of the 20-story building was completely collapsed, as you see on the picture. On the adjacent of 14-story building. So this collapse in general illustrates that the modern steel buildings are not every time can protect the citizen from the collapse, and they are also collapse during the earthquakes. Another example of the beams which show the problem after the earthquake. So this is picture was done in 1994 after the earthquake in Northridge. So actually it is typical example of a fracture at the moment connection. So in the previous discipline, metal construction 1, we discussed about type of connections, how can be connected beams to the columns. So about simple connection, rigid connection, moment connection, and so on. So here is a moment connection. And the paint brush is setting on top of the bottom flange of moment flange of a moment frame beam. The fracture is in the area of the groove weld that connect colored with the red, connects the beam bottom flange to the column flange. Next one is another picture from other earthquake. It is Hyojoken Nabu. It is in Cope earthquake in the 1995. So this is one of the examples of the fracture of a welded beam. So connected with to the column in the steel moment frame. We spend a lot of time of discussing how is important right design of the connection in steel construction, and these pictures illustrates that the most heaviest problems for the steel buildings actually happens near to the connection or in the connection, because it's most weak place in all steel constructions. This is connection, and connection not the beam with the beam, for example, like you see in the picture. So there are bolted connection, but the beam, for example, with the column. So because there are the various types of moments and acts to these plates and forces, various forces also act to the place of connection. So rigid, bended moments and so on. So here is example of the column also in the earthquake in Cope in 1995. So this is a fracture of steel box column. And actually in the modern steel high-rise building. So we cannot say that the collapses is happen only in the building which are old, for example. No, it's not right. Collapses can be found also in a new building because the steel or concrete or masonry buildings sometimes are not ready to resist the earthquake and are not able to protect building in the safety positions. And of course, it collapsed. So this slide reviews the basic concept of ductility. So ductility is ability of the structure or some elements or some structures of the building to withstand the large and elastic deformations without huge and significant loss of the strength. So we can say that ductility is an elastic deformation capacity. When the ductility of the building is on the higher level, the building will be show good results and being in elastic stage, but without any huge and significant deformations, without any losses of the stability, without any collapses. So, and during design of the steel buildings, it is important to make the good analysis and to know how to read the analysis of the steel buildings and see actually not in the stage in non in just in elastic stage, but in elastic stage. So also it is important to understand when minimum specified yield strength phi y, minimum specified tensile strength phi expected yield strengths R, Y, and the phi Y, and the expected tensile strengths R, T, phi U are used in the design processes. So, because all these parameters of the steel plays a significant role into the design of steel structures and the steel constructions. And pay attention during design on this minimum requirements of each these parameters is guaranteed us that the building will protect, actually steel building will will be protected by itself without any additional measures for protecting building from the earthquakes. So this slide provides an example of how values of the steel elements can be used in design of a brace and the brace connections in the steel resistant building. So the brace is the fuse, the member that designed to yield and the event of earthquake. So the required strength of the brace is determined from the calculation, from the analysis, typically the inelastic analysis of the frame using the code specified, using the Euro norms, where I showed the load combinations. Of course, during the design of steel construction, by using our programs for analysis of structure, we are also make the analysis with the load combinations. That's important, not only for forces, but for load combinations. So to size the brace for required strengths, which computed above, the design strength is of brace using the minimum specified yield phi y. So note that while the average actual yield stress will be greater than the minimum specified value. So it is fact and still possible to have the minimum specified value. So thus, when the sizing the brace code for specified loads, it's conservative to assume the yield strength of the brace material is again minimum specified value. So seismic provisions. So in this section, general requirements for bolted and welded connections that are applicable for all seismic lateral resisting frames. So for example, for main frames of the building, for rigid frames of the building, for collectors, diaphragms, and so on. So let's quickly look to the general positions. So bolted and welded connections are actually designed by the special requirements in the Euro norms and by the special specification and regulative documentations, because there are high responsibility for these structures. So the second statement above is the general reminder to the designers that ductility is a goal for the seismic detailing. The required strengths for non-ductile limit states in connection, like bolt fractures, like bolt fractures, plates, buckling plates. Um, they all should be based on the expected yield strength. And in general, it will assure that yielding of adjoining elements will occur before non-ductile limit states will occur in the connection. So, in general, bolts and welds do not share the forces in the predictable manner. So this is because welded joints are very stiff, and it will resist load immediately upon the application. Bolted joints in general are more flexible and require some deformations occur before the resistance is fully developed. Because of the stiffness, so mismatched between bolted and the welded joints, so they don't share forces, and the effective predictable manner. So, and consequently, the seismic provisions prohibit designers from the designed bolted and welded joints to share the same forces. So here is example of a connection in which an attempt is made to use both or bolts and welds to resist the same forces like earthquakes, like any lateral forces acting to the building, strong winds, and so on. For any seismic lateral resisting frame, portions of the frame are expected to yield and latch an elastic strain during an earthquake. So these portions of the frame are designed as and called as protected zones. So this section seismic provisions states essentially nothing can be welded, bolted, or shot pin attached in the protected zone. So the reason of the prohibition is that weld, bolts, or shot-in attachments in the highly strained protected zone may serve the fracture initiation sites. So the protected zone for each seismic framing system. So I told you of various of it, and you saw it before, are identified in the section of seismic provision for the framing system constructions. So the next slides so will show some examples and notes of protected zones. So here is one of the example of the protecting zone. So for the rigid system, so yielding during earthquakes is expected to occur the ends of the beam. Consequently, the beam are designed as protected zone. The next one. So for this system, very large and elastic strains are expected in the middle portion and at the ends of the brace. So as braces under the cyclic buckling. So consequently, these regions are also designed as a protected zones. And this final example for today lecture is the yielding in the frame system is expected to occur within the links. So the links in this system are therefore designed also as protected zones. So all illustrations which showed on this three picture show us how is important to design the protective zones in the bracing elements. So this zone during the lateral loads will accept most of the seismic loads. They will change in the shape. They will work in inelastic zone, but in the general, they will reduce the overall seismic load and will take it into itself, but will protect the main constructions from the buckling, from the collapsing. So if you have questions, because we have not so many time, about 3 minutes, I will glad to answer all of them. This presentation is not over, because we'll continue this presentation on the next hour lecture. There are no questions?
No.
Okay, if no, thank you very much.